If you want to fix user fatal message 9050, the most common way to do this is the following. If you're using Patran, go to the meshing tab here at the top bar. In the Fem Actions group of tools, click on equivalents. So that's this button here. If you hover over it, it says equivalents. Here on the right, it opens a new toolbar. Here, let me zoom into the model and clean some of this up. When you click apply, this is going to show you the nodes that have been equivalents. Now, if you go to analysis, entire model, and you rerun this analysis, you'll notice that in the new file, the error message is now gone. We've successfully performed the statics analysis. Now, if this equivalence option does not work, then this video is for you. In this video, what we're going to do is we're going to go into more detail regarding what this user fatal message 9050 means. We're going to go over the new versions of this error message. In newer versions of Nastran, it's actually called 10,030, and user fatal message 1031 or 10,031. Now, to keep it short, I'm going to refer to these user fatal messages as UFMs. The other thing we're going to be talking about is where am I getting this content from? There's a reference guide that you could refer to that I'll be mentioning in a moment. We're going to discuss what a mechanism is. I think if you want to really understand what this user fatal message is, UFM 9050, you have to know what a mechanism is. So we'll define that. And then what causes the mechanism? What causes UFM 9050 or UFM 10,030 and 31? We're going to go over some Nastran examples that cause user fatal message 9050. We're going to go over why specifically this is bad when you're trying to solve this equation F equals KX. What makes the mechanism really bad for this solution? And then we're going to talk about how do we detect mechanisms in MSC Nastran. If you look at the error message, part of the error message says excessive pivot ratios in matrix KL. What is a pivot ratio? You see this term a lot, but it's never really defined. So I want to take a few moments to define what a pivot ratio is. There's also another term that's often mentioned. If you look at the error messages, and here if I scroll down a little, let me go back here, and let me see if I can undo those. I guess I can't. Let me see if I can. In the error message, you see a lot of these terms. Maximum matrix to factor diagonal. Matrix factor diagonal ratio. What is the factor diagonal? What is this ratio that keeps being referenced in this document or in the F06 file? So we're going to take some time to define what that term is. How do you get that value? And then towards the end, we're going to go over how do you interpret this table? How do you interpret this message? How do you interpret this grid point, DOF, degree of freedom, this ratio, and this matrix diagonal? Where are these values coming from? So in this video, we're going to discuss where they come from, why they're important, and how do we fix UFM 9050, 10,030, and 10,031. Okay then. So we just went over the most common method. I'll explain why this method worked in a moment. But now let me go over the various versions of this message. So in older versions of Nastran, this message is known as UFM 9050. In newer versions of Nastran, I don't know what specific version it was. The version number, or rather the error number, is different. It's UFM 10,030 and UFM 10,031. The messages are slightly different, but they all mean the same thing. You have a mechanism. Your solution cannot be performed. So now, let's briefly talk about where I'm sourcing this information from. Whenever you speak to a Nastran user, one of the first things they'll tell you is read the manual. And when you do that, you'll find that they do discuss what a mechanism is and why this causes an issue when you're trying to perform your statics analysis. So if you look in the MSc Nastran reference guide, if you look in this section, mechanism type singularities, you are taken to this section. So here, the search I think is taking a little longer, so let me see if I can find it here. Or we'll just wait for this to finish. Okay, that search took a lot longer than I was expecting, but here in the reference guide for MSc Nastran, you get this section, mechanism type singularities. This describes some of the information I'll be going over in today's video. So if you want to read up on this, I refer you to this document. Okay then, so now what is a mechanism? So here, let me see if I can use my tablet properly today, and give me a moment while I track down the stylus. Right, so let's go over what a mechanism is. So let me change the color. So here, let's go ahead and draw out what is a mechanism. So here, let's draw a very simple cantilever beam. You apply point load at the free end, and this will deflect like that. Now, suppose I have the same cantilever beam, or just the beam, and I apply my force. Here, what the beam will do, it will translate. So this is going to be its new position. And you can see that there's a difference between both of these examples. In this example, you have deformation in the material. So this is not a mechanism. And then here on the right, there is no deformation in the material. So there's no deformation. So this is a mechanism. So a mechanism is you have movement without deformation in the material. Now, let me give you another example. Let me see if I can add another one here. So suppose we have another beam, something like this. We'll have rollers. And suppose we have a load here at the midpoint. So we'll call this F. This is an unstable structure. And that's because if you do your equilibrium checks, you'll find out that the sum of the forces, at least in the X, are not equal to 0. So what happens here, you apply your F, and then what happens? The whole beam moves as a rigid body. So let me see, how can I show you this? So maybe we'll have some extended ends here. So let's suppose that the beam has a little bit of extension here. So when it moves, it might look something like this. And then, right, so this is before loading, and this is after loading. So you can see that with this load, since the boundary conditions are unstable, the sum of the forces are not equal to 0, this is going to move as a rigid body. There is no deformation in this scenario. So this is what a mechanism is. It means that you load it and it doesn't deform. It just translates or rotates without deformation. Okay, so going back to the agenda here, now let's go ahead and talk about what causes mechanisms. So the most common reason is equilibrium is not satisfied. So let's go ahead and talk about that real quick. So this is going to be the most common reason why you're getting UFM 9050. So 9050, it's unstable. So if you go back to that example where I have the beam on rollers, that is not okay. So again, if you do the sum of the forces in the X, the Y, and the Z, You have to make sure that they're all 0. You do the sum of the moments. Also, they all have to be 0. In this case, they're not 0, so this is not okay. Now to fix this, what would we do? Here, I could use a pin and a roller here. And then here, if I do the sum of the forces in the X, the Y, and then the moments also, both of them are okay. So in this case, this is stable, and this is not stable. Now there's another scenario that's worth mentioning. I'll call this unstable B. Sometimes when you mesh in your tool, your FE program, so here let's go ahead and add a pin and then a roller here. So this is going to be my X and my Y. Suppose you mesh it and it looks like this. Now when you try and perform your statics analysis, you get the error UFM 9050. You ask yourself, okay, what's going on? My boundary conditions yield a stable configuration. What is going on? If you're not careful, the mesh could actually be disconnected. So here, let's go ahead and see if I can draw it. So the red is the deformed mesh, if you will, and the black is the original mesh. So when you look at the black mesh, the mesh looks like it's a fully continuous mesh. There are no pieces in the mesh. It's all one piece, if you will. But if you're not careful, your mesh could actually be 3, 4, or some other number of pieces, if you will. So here in this case, what happened was that the middle part of the mesh was actually disconnected from the rest of the mesh. So here I've actually moved it here to illustrate that since this portion of the mesh was not connected to the other meshes, it's actually kind of floating if you think about it. This will also cause UFM 9050. I'll call this the detached scenario, or the mesh detached mesh. So let's go ahead and write that detached mesh. So again, if equilibrium is not satisfied, you get an unstable structure, you get user fatal message 9050. If a mesh is detached and it's not connected, this other loose mesh is also unstable, so you also get UFM 9050. Now, what I did before this presentation is I looked up these two animations just to show you and just to emphasize how important it is to support your structure. If you don't support your structure, it's not going to be in equilibrium. If it's not going to be in equilibrium, you're going to get that user fatal message 9050 and 10,030 and 10,031. So if you have an unstable mesh, you get those user fatal messages. And now the second scenario, when you get 0 or nearly, or rather the second cause of a mechanism, let's go over that really quickly. So we'll go to the beam example again. So we'll draw our beam here, but this time we'll do this. We are going to support this beam on 2 springs. And then here, let's put a roller here. And then, right, so this should be stable. Question mark, is it stable? If you do your summation of the forces and the moments, it is stable. But now let's do this. Let's suppose that K1 here has a very high stiffness, maybe 1 times 10 to the 10, and then here K2, it's a very small stiffness of 1.0. So you can see there's a big difference between both of these stiffnesses. Now this is K2 equals 1. Suppose here I put a load or a force of, I don't know, 1 million as an example. So here we're going to write 1 million. Okay then, so roughly, if F equals Kx, and I know my force is 1 million, and then I know K is 1, then my deflection is going to be a 1 million. Now if the length of this beam is maybe, I don't know, 10 meters as an example, here my deflection is approximately 1 million meters. That is not okay. So this is a scenario where you're mixing stiffnesses that are of different magnitudes. So what happens in this scenario? So let's go ahead and write another page. And we'll go ahead and draw our spring here, another spring here. It's basically the same scenario we had in the previous slide. I'm going to draw our force here. After deformation, this spring K2 is so soft that this beam is just rotating, if you will. And it's not deforming, it's behaving as a mechanism. So this is when your stiffness, something in your finite element model has a very small stiffness. It's either nearly zero, or it's actually zero. So if you have one of these situations, you will have a mechanism where the model does move, but it's not deforming. And then here, let's go ahead and come up with another example. Let's suppose that I have this beam, and then my boundary conditions yield a stable structure. But this time, what I'm going to do is I'm going to use different materials for this beam, if you will. So here we're going to use one Young's modulus that has maybe 200 E9 pascals. So this is its stiffness. Here, this material will also be 200 E9 pascals. And then E2, what if I make that 1? So here you can imagine this is steel, but this is maybe jello or gelatin. Now, what happens when I load this with, I don't know, 1,000 newtons? So what we're going to see happen here is this portion is going to remain essentially the same, if I remember correctly. It's going to remain stiff. It's going to behave like a rigid body. But then here, for the middle portion of this, it's actually going to deform a lot. So what's happening here is that even though we do get some deformation, part of the structure is actually behaving as a mechanism. So this is another situation where if your stiffness here in the bottom right, if it's close or equal to 0, that's going to cause another mechanism that's going to cause user fatal message 9050 in your F06 file. Now what I have here are some examples. So let's go ahead and take a look at these examples. So in the first example, this is going to be the unstable boundary condition scenarios. So here, unstable. So here, just to save some time, let me draw this out so you see what's happening. So here what I've done is I have a roller here, a roller here, a roller here, and a roller here. Now, if you go through your summation of the forces, now one trick to determine if you have an unstable or unstable configuration is to do the following. First, define your boundary conditions. Now, this is a trick that one of my professors taught me a long time ago. You apply 3 fictitious loads on your structure. So pick a point, preferably somewhere away from the boundary conditions. So here, maybe at the top, we'll pick this point, and then we're going to apply a load. So here, maybe this is the X, this is the Y, and then this is the Z. So here, we're going to apply a fictitious load in the X. So f of X equals 1. We're going to apply another load in the Y direction. So Fy equals 1, and then another load in the Z. Fz equals 1. Then with a piece of paper, you do your equilibrium checks. So what's going on in the X? If I apply a load of 1 plus my reactions, and my reactions are not, I don't have any reactions, so it basically goes down to 1. This is not equal to 0, so this is not okay. So this is unstable. And then you do the same for the other directions. So is some of the forces in the Y, the Z, are they all 0? And then for 0, 2, I believe this is not 0 also, so this is not okay. And then you do this for the moments too. Now this is a thing you do with a piece of paper and a pencil. You don't have to do this with a computer or MATLAB. This is all hand calculations at this point. So this is okay. This is not okay. And then this one. Okay, now there might be a mistake here, but I think you get the idea. So number 1, apply your boundary conditions, and do this on a piece of paper. Draw your free body diagram, apply your boundary conditions, your supports, add some fictitious loads, unit loads in the X, the Y, and the Z. Go through all of your equilibrium checks. Make sure everything's in equilibrium. If one of these equations fails, then you have to fix that before moving forward. And here in PARAM is that first example where you don't have a stable structure. So let me go ahead and show you what I mean by this. Let's go ahead and turn some of this off. Let's make this black maybe. Right, so here you can see that I've constrained the second degree of freedom, which is in the Y direction. So here I'm only supporting this in the Y direction for these 2 nodes, and the same for these 2 loads. And then for the load, in this case, I'm having a pressure distribution. So if we run this with Nastran, let's go ahead and do that real quick. If you go ahead and run this with Nastran, you will get that user fatal message. So let's go ahead and pull it up real quick and scroll down a little. So here, user fatal message 9050 run terminated due to excessive pivot ratios in matrix KL. Now, I was going to hold off on how to debug this, but maybe I'll do this as we go through these examples. So how do you debug this message? Okay, so number 1. The easy way to do this is to do the following. So I'm going to close this old PARAM window. Perform a normal modes analysis to debug this issue. So here, if we go back and we perform the normal modes analysis and click apply, this is now going to perform a normal modes analysis instead of a linear statics analysis. Now, the benefit in doing this, let me go ahead and attach the results. The results, the mode shapes can tell you which are the mechanisms, if you will, which are the rigid bodies. So here is one of the first mechanisms, or rigid bodies. So here, if we animate this a little. So remember, this is a structure supported on some rollers. So you could think that this structure is allowed to move left and right along the z-axis. So this is the first rigid body. So this can help you determine, okay, this structure is not supported in the z direction. So that's a problem. We have to fix that. Now, when you look at this, every rigid body is going to have a natural frequency close to 0. Here, you don't get exactly 0. Here on the right, you get 4.99 e negative 5. So let me go ahead and pull this up real quick. So you get 4.99 e to the negative 5. This is very small. It's equivalently 0 here. So now let's go ahead and take a look at the next rigid body, which has a natural frequency of 0. So let's go ahead and click apply here. Slow this down a little. Now, all of these rigid bodies are indicating the same thing. Since I have this structure supported on only rollers, this structure is allowed to move left and right from this perspective. And then we'll go ahead and look at the last rigid body. So there are 3 rigid bodies here. So this is the third natural frequency, the third mode shape, the third rigid body. But then after this, this is the first non-rigid mode shape, if you will. So here, from this perspective, you can see that this is properly supported, but in the other cases, it's not. So how do we fix this? The mode shapes help in some cases. Actually, they help a lot of the time. But here, we go through the equilibrium chart. We draw our free body diagram. We draw our supports. We draw our fictitious forces. We go through the equilibrium equations. We find out which equilibrium equations are not satisfied, and then we add additional supports. So what I'm going to do next is the following. So this is going to be the same beam, but this is what we're going to do. We're going to still have some rollers here, but we're going to create some pins here. So in order to create a pin, what do we do? Here you can see that the displacement, or the translation along the X, the Y, and the Z. So remember, there's a degree of freedom here. So there's going to be, this is going to be the first degree of freedom, this is going to be the second degree of freedom, and then this is going to be the third degree of freedom, and the same thing for the other ones. 1, 2, and 3. So how do we get a pin here? So I'll call this node 1. So node 1, how do we get a pin at that location? So the translation along the first degree of freedom, that's going to be 0. The translation along the second degree of freedom, that's going to be 0. And then the translation along the third degree of freedom, that's going to be 0. And we're going to do this for the other node. So node 2, I don't know what the node numbers are, but we'll figure that out in a moment. So right now, the rollers are the following. Rollers have this. The translation along the second degree of freedom, that's 0. So let's go ahead and take a look at this in Patran. So if you look at the supports here, I have one called rollers. If you look here at the middle, you see that the first degree of freedom is blank, so it's free. The second degree of freedom, we specified a translation of 0, so this is a support. And then the third degree of freedom is also free. And then if we turn this on, you can see that we have rollers at these 4 corners. Now, how do we define a pin support? So here I'll call this pin B. And for the input data, like we mentioned a moment ago in this document, we just want to make sure that the first, the second, and the third degree of freedoms are 0. The translations are 0. So then go ahead and select maybe the nodes. So nodes, these ones here. And let me make sure I'm picking the right nodes. Let's go ahead and do that. Click OK and then apply. Okay, perfect. Now remember, before we had this error message, so user fatal message 90. Oh, am I looking at the right one? Right, so before we were getting this message, user fatal message 9050. And now how do we fix this? So we've added the supports. Now let's go and redo this analysis. So we'll go ahead and click entire model, switch this back to linear statics, and we'll click apply. And let's go ahead and make sure that that error is gone. So if you go through this, you'll notice that now we get some displacements, some loads, and that user fatal message 9050 is no longer here. So it's a good sign that we're in the right direction. So let's go ahead and import the results. Let's go ahead and look at the deformed shape. And let me do this. The reason this is happening is because I'm pointing to a different model. So let me go, or I'm pointing to a different H5 file. That other file was moved, so I can no longer look at the results for that other file. So I deleted that other H5 file. Now I'm only left with one load case here. Let's go ahead and look at the translations. So now I can get a solution once I fix that unstable structure. I put the proper boundary conditions. So to quickly summarize, I took a piece of paper, I wrote out my supports, I added 3 fictitious loads, I went through my equilibrium equations, I found out which equations are not satisfied. I then went ahead and added enough supports to yield a stable structure. I then performed the analysis and the error is gone. So that's the first example. So let's go back to the agenda. And now let's go ahead and talk about the second example when you have a detached mesh. So let me close this Patran window. And let me open this other Patran example. And when you look at this model, it's going to look like it's one continuous mesh. And if you remember at the very beginning, I said that the most common way to fix this issue is to go to meshing and click on the equivalence button and click apply. This is the scenario where this equivalencing works. And now I get to describe why it works. So let me go ahead and do the following. So here's our same beam, pins, and rollers. There's a pressure load at the top. Let's see. Now let me go ahead and run this just so we can see the error message. So if you look here, solution type, linear statics, and click apply. And then if we look in that directory, if we look at the F06 file, we get the same fatal message, user fatal message 9050. So here it is. User fatal message 9050, run terminated due to excessive pivot ratios in matrix KL. Here we get this table. Now here, let me quickly talk about how do we interpret this table. First, look at these node IDs. So here we're looking at the following node IDs. Let me move this to the side. So here, let's look at node 52, 281, and 285, and 545. So this is typically what I do when I see a node in this table, rather. So what I do is I find the node. So say this is node 52 or grid 52. So this is node 52. What I do is I look at the surrounding area of the mesh. And then I ask myself, why is this a mechanism? So remember, there's deformation, or there's motion with no deformation. That's what a mechanism is. So why is node 52, why is the surrounding mesh, why is that very stiff. It's not deforming. What's going on here? So if we go back here, and let's go ahead and find out where these nodes are. So I'm going to go to the Utilities, Display Fem Label tool, and we'll go ahead and type in node. Go ahead and clean this up a little, click Apply. So these are the nodes that are giving us problems, but it's not the nodes themselves that are giving us problems. It's the surrounding mesh that's giving us problems. So why would this region, and this region give us a problem? Now, again, the easiest way to diagnose this issue is to go to a normal modes analysis. So let's go ahead and do that right now. And then after that's done, let's go ahead and import the H5 file, and let's go ahead and look at the mode shapes. So when you have a natural frequency very close to 0, that means you have a rigid body. These rigid bodies or mechanisms can clue you in on what's going on. So here, let's look at the first mode shape. So this is the first mode shape when it's not animated. Let's go ahead and animate it. And so here is the issue. This center region of the mesh is not attached to the rest of the model. This mesh does not have enough supports for equilibrium, so this mesh is unstable. Here, let me do this. Let me go ahead and redo this again. So here, I think this would give you a better idea of what's going on. So again, this is a detached mesh. And here, let's go ahead and cycle through the other 0 hertz mode shapes. So here, remember there are rollers here. So since there are only rollers here, this is essentially almost like a pin connection, if you will. Let's go ahead and look at the other rigid bodies. Right, so that's also a pin. So remember, we looked at these nodes. So these nodes again came from this table. So if you look at this table, this is node 52, node 281, 285, and 545 and 546 in that case. We went to the model, we found where the node is, but then we looked at the surrounding mesh and we asked, okay, why is this a mechanism? Why a mechanism? So then we perform a normal modes analysis. And then we were looking for mode shapes that are 0 hertz. And when we find these mode shapes that are 0 hertz, it's clear what the mechanisms look like. It's clear what's going on with the mesh. So here, okay, so we know that this mesh is detached from the rest of the model. In this case, when we mesh this this geometry, let me show you the geometry. The geometry was actually 3 separate boxes, if you will, box 1, box 2, and box 3. So we mesh this, but if you look carefully at the interface, so here you have node 208, 256, but if you look carefully here, there are 2 nodes that are overlapping here, and that's why you cannot read the label. There are 2 numbers overlapping each other. There are 2 nodes here. Now, if I zoom out again, let me go to this other region. This region also has overlapping nodes. And what makes it hard for us is that when we look at the mesh, it looks like it's one continuous mesh, but it's not. So when we go to meshing and we click equivalence and we click apply, what that's doing is the following. Those overlapping nodes are now merged into just one node. So if there were 2 nodes here at this point, there's just 1 node. So this helps make a fully attached and continuous mesh. So I've done that equivalence now. Let's go to the entire model, click on solution type and click linear statics, click apply, and click yes. And if we look in the F06 file, you notice that the user fatal message 9050 is no longer here. I actually get some results regarding what the displacements are and what the loads are. And then here, just to make the point again, let's go ahead and do a normal modes analysis. And let's go ahead and look at some of the mode shapes. Let's go ahead and look at the results. And if you look at the first mode shape, you see that the natural frequency is 7. It's not 0 like it was before. And let's look at the first mode shape. So this is what the first mode shape looks like. Maybe let's go ahead and animate it a little. So remember, there's a pins on the left and then rollers on the right. So you can see that the mode shape, it makes sense. And then we'll look at the next mode shape. You can see there's bending. This is a bending mode. And then here, you know you have a stable structure when the natural frequencies are greater than 0. Okay then, so let's go back to the agenda. And let's quickly summarize what I just went over. So again, when you see this table, and I don't think I have it anymore. I guess I don't have it anymore. Let's see if I can find it here. Right, so here's that table we had a moment ago. So when you look at this table, first look at the node IDs. And then when you're looking at those nodes, don't look at just the node. Look at the surrounding mesh. And then ask yourself, why is this region a mechanism? Why a mechanism? And then here we went through a normal modes analysis. We looked at the 0 Hertz mode shapes, and then this helped us identify what the mechanisms are. And then after that, we added some supports to make sure that we had equilibrium in the structure. Okay then, so let's go ahead and now talk about the next example. So in these examples so far, it's been an issue of supports. But you can also get a mechanism where you're dealing with 0 or nearly 0 stiffness. So let's go ahead and look at an example of this. So let's go ahead and open this example. Now in this next example, we have this beam with a pin. It's got a roller, and then we have a pressure load at the top. I'll call this P. And then what we did here was something a little different. This part of the beam and this part of the beam, the Young's modulus is very high. So 200 gigapascals, if you will. But then here in the middle, we gave this a really small stiffness, maybe 1 Pascal. So let's go ahead and see what happens here. So here, let me show you those examples actually. So here's our beam. Let's look at the first stiffness. So here, this is going to be 200 gigapascals. And then the next stiffness is going to be 2 actually. So let's go ahead and modify this. So here the second material has a stiffness of 2 pascals. Now let's go ahead and run this statics analysis. Let's go ahead and run it, and then let's go ahead and open the F06 file. And then we scroll down, and we get the same user fatal message. User fatal message 9050 run terminated due to excessive pivot ratios in matrix KL. Okay, that's okay. Let's go ahead and do this. Let's go ahead and take those node IDs, those grid IDs. Let's go ahead and move them here. So what I want to do is create a list, because we're going to go ahead and look at the node IDs in Patran. So let's go ahead and display those nodes. I'm going to hide the mesh a little. Okay, so again, find the nodes, then go and do the following procedure. So find the node, look at the surrounding mesh, and then ask yourself, why is the surrounding mesh a mechanism? What's going on here? Why are we getting a mechanism? So here, let me draw some lines for the mesh. So like before, what we're going to do is perform the, how do I say, normal modes analysis. So let's go ahead and do that. So we'll go ahead and click on normal modes and click apply. Click yes. And this one's taking a while, so let's go ahead and wait. Okay, now let's go ahead and attach the results. So now the rigid bodies, like have been mentioned multiple times, the natural frequencies are very close to zero. So here, the first mode shape has a very small natural frequency. It's 4.96 times 10 to negative 5. So let's go ahead and animate this first rigid body. Okay, so here things look okay. There's not a lot of useful information in this example. So then let's go ahead and move on to the next mode shape. Click animate. And then here, right, so this still doesn't, it's very subtle, but I think it would help if I pause this. You'll notice one thing here. You notice this region here. Let me just maybe take a screenshot of this. So here I've taken a screenshot of the mode shape. And one thing you'll notice in this example is that this, and remember, this is node 46, 525, 526. And these are the same nodes that were found in the table, the table with all the problematic grid IDs. So this node, so this would be this node, and then this node, I believe. And then you look at the surrounding mesh, you ask yourself, okay, why is this a mechanism? If you look carefully at these regions, you'll notice that this portion of the mesh, this face, if you will, it's straight. It's it looks almost like it's stiff. I don't know if that's the right word to use here, but this should not be happening. What should be happening is you should have a continuous deformed shape like this. It looks parabolic. It should not be straight, then parabolic, and then straight again. So you can see in this mode shape, it's very subtle, but some of our structure is very stiff, while the other part of the structure is actually very soft. So here, if you remember, the stiffnesses were 200E9 pascals, and the other one was 2 pascals. So here I like to joke sometimes that, okay, this is steel, but this is jello. And for those in Europe, this would be gelatin. Jello is a very popular form of gelatin here in the US. So again, in this other scenario, what's going on? We have a difference in the stiffnesses. So here we have a very, very stiff, and then versus a very soft stiffness, right? So why is this a problem? This is a problem because part of the structure is going to remain almost in an undeformed state. So here, it's still perfectly rectangular. It's not deforming for the most part. The same for this. It's still, it's almost a mechanism, but here we get some deformation. So this was flagged to us. This is why we got the user fatal message, because of the very high and very low stiffnesses that were being used in this structure. Now, what do you do in this case if you want to fix it? Here, just increase the stiffness, and then that should work. Now, one other thing, if you really want to go forward with the solution, if you want to skip and bypass that user fatal message, you can do the following. So here, what I'm going to do is manually, or before I do this, let me make sure this is a statics analysis. Click apply. Now, how do you bypass this message if you want to go forward with it? You could do what's called PARAM BAILOUT -1. So let's go ahead and copy this. Let's go ahead and open that bulk data file. Let's go ahead and paste it here. And if we look at the F06 file, so we still get that user fatal message, but now we've added PARAM BAILOUT -1. Let's go ahead and run Nastran with that PARAM BAILOUT entry. Now, if we look in the F06 file, that UFM is now gone. And we have results. We have displacements here. And now you might be asking, okay, what do the displacements look like when we use this PARAM BAILOUT -1 entry? So here I've attached the results. Let's look at what the deformations look like. Oh, let me turn off the animation. Okay, right now we're looking at a scaled version of this deformation. Let me turn on the true scale. So look what happened. Look how much deformation there is in this example. So our beam is here. Wow, this is very big. So this is our beam before deformation. Now, this is what the deformation looks like in this scenario. So we zoom out. Look how large the deflections are. All because I mixed up the stiffnesses. I had steel, and then I mixed it up with the jello stiffness. And look how massive our deflections are. And actually, let's go ahead and look at what the dimensions of this beam are. So let's go ahead and show the distance between this point and this point. So this beam is around 15 units of length, but then our deformations are on the order of times 10 to the 6. Right, so if you look at the deformation here, it's deflected 2.65 times 10 to the 6, but our beam is only 15 units of length, so this is a big problem for us. So again, here, how do you fix this? Just simply type in a reasonable stiffness. So here we'll go ahead and type in 200E9, click apply, go to analyze and do all this. And now if we look at the F06 file after we fix that material, you can see that we no longer have the user fatal message 9050. And then if we look at our deflections, they're a lot smaller now. So if you recall a moment ago, I think it was 2.54 e to the, what was it before? Was it 6, I think? Right, I think it was 6. I think it was 2 times 10 to the 6 before, but now it's on the order of times 10 to -5. So that's more reasonable. So if we want to, let's go ahead and attach the results here. Let's look at the deformed shape. And this is going to be the true scale. So let's go ahead and zoom in a little. So you can see if this beam is 15 units of length, our deflection is now times 10 to -5. So it's very subtle, the deflection. If I want to, I can scale it. And so that's what the scaled deformation looks like. So now this is how we address it in a situation where we mixed up the stiffnesses. We have very high and very low stiffness. Now there's another scenario I wanted to demonstrate. So let's go ahead and come up with another example. Now so far we've been dealing with 3D elements. And the same scenario or procedure is going to work with 2D and 2D elements. When you're dealing with 1D elements and 0D elements, the procedure is still the same, but sometimes it's a little bit difficult. So I'll do my best to come up with an example that's one-dimensional or zero-dimensional, actually. So let's go ahead and do this. In this example, this is what we're going to do. We're still going to be dealing with the same beam. We have a pressure load here at the top, so pressure. But here what I'm going to do is I'm going to support the translation along the Y with some springs. So here, the springs in this case, they're going to be defined with CELAS entries. So this is going to be a type of 0D element. So what I'm going to do here is for the first stiffness, it's going to be really high, so maybe 1E9. And then here for the second stiffness, maybe do K2 equals something very small, maybe 2.0, like the last example. Now, here I want to show you how we debug this scenario. So let's go ahead and open this example in Nastran. So that would be this example. So let's go ahead and open it up. And let me open the F06 file actually. So if I look at the F06 file, I get the same user fatal message. User fatal message 9050. So here's that model. And then I've already taken the time to put the springs on here. The springs are represented with these markers, these triangles, if you will. So these are the springs. Here, let me turn on the boundary conditions. Right, so here are the supports. I won't go over that, but now let me look at the spring stiffnesses. So let's go ahead and look at that. So here, if we go to the 0D branch and we look at the stiffness. So one of the stiffnesses is about 9 or 10 E10. So let me do this. Let me go back here. So here the first stiffness is 10 E10. Oh, this is actually not in pascals. It's in Newton meters. I think before it said... Let's see if I can find this example. Oh, okay, that's all right. Right, so these are in units of force length. So the first spring has a very high stiffness value. Now, what about the other spring? How soft is that other spring? So if we look at this, it's 1. So here, we're actually using a spring value of 1 E10 Newton meters. If this was in units of Newton meters. Oh, sorry, this is just 1 Newton meter. So you can see there's a big difference in these stiffness values. And now why is this a problem? So here on the left is the beam. And then here's your pressure load. So here on the left is the current setup that we have. But because this spring here is very, very soft, it's equivalent to this scenario. It's almost as if the spring is not there. So this is not stable or unstable, so we're consistent. So this, in this case, since that spring is essentially negligible, we have an unstable scenario, and then we get that user fatal message 9050. So now let's go ahead and take a look how to debug this. So if we look in the F06 file, there's only one grid ID in the table. So here, node 46. Where's node 46? Let's go ahead and display that node. Node 46. Click apply. And here I have to type in node 46 and click apply. Okay, so node 46 is here. So remember, it's not the node that you should be looking at, it's the region around the node that's important. So here in the middle is node 46. And then here we ask ourselves, for the surrounding mesh, why is it behaving as a mechanism? So again, why mechanism? So what do? We do the same process as before. Instead of doing a statics analysis, let's go ahead and do a quick normal mode analysis. And let's go ahead and attach the results. And then our rigid body modes or our mechanisms are going to be defined with the 0 Hertz frequency. So this is a mode 1. You'll notice that the natural frequency is actually somewhat large. It's 0.003. This is still small relative to the other natural frequencies. So here you have a 283, 281, 164, 147. But this one's very small. The natural frequency is very small. It's suspicious. So let's go ahead and display what that mode shape looks like. And here you notice that, hey, I have springs here on the left and here on the right, but why is the mode shape like this when this stiffness should be very high also? So here, this is giving me a clue that this spring is very soft. And then here I go back and I look at the 0D stiffness. So let's go ahead and copy this. And let's replace the old stiffness. Click OK and click apply. And now let's go ahead and rerun this with a linear statics analysis. And let's go ahead and attach the results. And then if we open the F06 file, you notice that the UFM 9050 is no longer here. So now we can actually import the results and look at our deformed shape. So this is our deformed shape for this example. Okay then, so I think that was the last example on the agenda. Right, so to quickly recap, remember back to these animations. It's important that your structure is stable, that there are enough boundary conditions and supports to have equilibrium. In cases where you use a very soft or very low stiffness, this can actually cause a nearly unstable structure, as we saw in the last example. So 1, make sure you have enough supports for equilibrium. Number 2, make sure the stiffnesses are consistent. And now let's go to the next part of this agenda. Okay, so now mathematically, why are mechanisms bad? So the whole goal with linear statics is to solve this equation. Today I want to use F equals Kx. Now part of this involves finding the inverse. Now sometimes the inverse is undefined. Now what does it mean to be undefined? Here, let's go ahead and draw an example here. So we'll draw the beam again, but this time we'll have some rollers here. And we'll apply a load F. If you look carefully at this, there are multiple solutions for this example. One solution could be, how do I do this? Actually, let me redo this. Let me do this with a line, actually. So here, let's go ahead and draw a line. Here is our force. So this case, this scenario here, you'll notice that number one, it's unstable. But if you really wanted to, you could actually get a solution. One solution for this could be something like this. Let's go ahead and maybe draw it. So you notice that this end has translated a little. So this is solution one. And now what's another solution here? This could be another solution here. So you notice that these two ends have moved a little also. So you notice that both of these are solutions to this equation. So I think this example may have been a little confusing, but hopefully you get the point. There should be only one solution for k-1 to exist. If you have multiple solutions, then k1 is undefined, it doesn't exist. Now, if you look back to those animations I showed a moment ago, here in these cases, k1 is undefined. So this is why it's bad to have a mechanism. The inverse of k is undefined. There's no solution, so that's why a mechanism is bad. Okay, then let's go on to the next example. Now, how are mechanisms detected? Here, let's go ahead and quickly talk about pivot ratios. So a pivot ratio is the same as the following. Let me go ahead and copy this, actually. If you look in the F06 file, yep, let me go ahead and look at the old. So if you look here in the old message, you see the term pivot ratios. So here, let's go ahead and talk about pivot ratios. Specifically, let's talk about this matrix factor diagonal ratio. This comes up a lot when you have this UFM 9050. Here, factor diagonal, max ratio of matrix diagonal to factor diagonal. It comes up so much, and now we have to ask ourselves, what is this term? So let me see if I can paste it here. Although it's never stated in the documentation, I'm left to assume that pivot ratio is the same as this matrix factor diagonal ratio. So now we have to ask, what is this ratio? This ratio is the following. When you have k, during the solution, k is expressed as the following set of matrices. And then this transpose. So LD transpose L. And now what the matrix factor diagonal ratio is the following. So here, I don't know, I'm just going to come up with some examples for k. So maybe k is a 1.0, 2.0, 3.0, so on and so on along the diagonal. And then in this case, all the other values are 0. In this case. And then so it's going to go ahead and find L. It's going to go ahead and find L transpose. And then here in the middle, we're going to have a diagonal matrix with other values. So here I'm just making these up right now. Maybe 8.0, 9.0, 10.0, so on and so on. So what this expression is the following. This expression, I'll call it ratio for now, is equal to KII over DII. So we're the i's are the rows and the columns, and then we're only focused on the diagonals. So here, as an example, take this first term. So this is going to be I equals 1, 1. So row 1, column 1. So here in this case, it's going to be equal to 1.0. Here, if you look at the D matrix, it's 8. So we're going to divide it by 8. Now, again, this is all coming from the MC Nastran reference manual. If you look at this document, if you look at equation 732 in this document, the ratio is defined here, KII over DII. So here, the ratio in this case is 1 over 8. Now, why is this ratio very important? If it's very high, if it's greater than the default of 1E7, this is indication, if this is true, then you have a mechanism. So that's what these ratios are used for. This is why you have excessive pivot ratios, because you have a mechanism. So let me go back to the notepad file and see where we're at. Let me move this a little. Got too many windows open. Okay, so how are mechanisms detected? Right, so pivot ratios, they're the same as those matrix factor diagonal ratios. And I think it might be worth exploring an example here. Right, so just to prove to you that this is true, let me do this. Let me close this old window. Let me take this example. Right, so we have this table. If you look at this table, let me do this. Let me copy all of this. Let me do this. So let me copy this to this file. So let's go ahead and do this. The formatting is a little off here, so let me see if I can fix this for you. I'm looking for something that's a little cleaner here. I don't know if I'll be able to. Oh, yes, perfect. There we go. So here what I want to do is annotate this text for you. So let's look here. And let's read this real quick. So we get this value, maximum ratio matrix diagonal to factor diagonal. So remember, this is going to be KII over DII. So this is the ratio. So here, what they're saying here is that the ratio in this case, the ratio is equal to 6.5 E15, and you can see it's very, very large. It's greater than the default of 1.0 E7. So we have a mechanism here. So now, if we wanted to, we can look at this other table here. And so here in this column, these are going to be the ratios, KII over DII. This matrix diagonal, this is going to be KII. And then this is going to tell us the node ID and the degree of freedom. So now, if we look here, imagine that this is your stiffness matrix. So there's a value here, 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 here. At this point, let's focus on this row. So for now, do I have a highlighter here? Let me just focus on this row for now. So here, if we look at the stiffness matrix, at row 229, if you look here, at row 229, so here, and I'll put 229 here, the stiffness at that element, if you will, or not element, but that row, column 229, it's going to be equal to 2.969 E10. So here, the matrix diagonal, this is K at that value. And now if we look at, well, I guess at this point we don't have D yet. What is D here? For this example, I'll call this K299. So this is equal to 2.969. What is D? 299. So what is that? What is that in this case? So what we're going to do now is the following. So let me go ahead and do this. So I believe let's go ahead and divide this. So right now I'm taking these two values and I'm back calculating D. So D is supposedly this. So let's go ahead and confirm this is D. Oh, I think I mixed it up. So let me look at this real quick. I flipped this wrong, so let's go ahead and do this. And sorry for the delay here. This is the first take of this video, so that's why it's a little rough around the edges. Okay, here we go. So here my diagonal is a 4.55. So let's go ahead and write it here at the bottom. So far I've back calculated it. 4.55621, and we have 1, 2, 3, 4, 5, 6, and 7. So E -7. So this is what the diagonal term is. Now how do we get the diagonal term from Nastran? Just to confirm that we are doing the same math that Nastran is using, we're going to have to go into this alter. So in a separate video, I'll go ahead and briefly discuss how we work with DMAP. So here, this DMAP alteration, if you will, this is going to output the D matrix for us into the F06 file. So let me go ahead and run Nastran for this example. So let me show you the F06 file real quick. So if you look at this F06 file, we only have the user fatal message 9050. So now when I run it, after I add those DMAP statements or that alter, if we look at the new F06 file, and let me make sure I'm doing this right. Go ahead and do this again. Okay, let me delete this and rerun this. So run Nastran. I guess it's not working in this case. So let me try this. This is supposed to print out the diagonal matrix, but it's not. So let me see if I can force it to print the diagonal matrix with PARAM BAILOUT -1. Ah, here we go. Okay then. So it was not outputting the D matrix for me. So this is to quickly summarize. Here I added this set of DMAP statements to alter the solution process. Here I want to print the D matrix. That didn't work. It was terminating with user fatal message. So what I did was I forced it to continue the solution with PARAM BAILOUT -1. So now if I scroll down after this table, here it says matrix D. So this is the diagonal matrix, and we only get the diagonals here. We don't get all the zero terms. So if I scroll to the very bottom, and this is a very big example, so let's go ahead and scroll to the end. And the very end is going to be the diagonal term for row 299. So if we go back here, we back calculated here at the bottom right that the diagonal term is 4.55 e -7. And here I counted the wrong number of decimal points. So let me go ahead and do this. At the bottom right, let me fix this. Let me make that -6, not -7. So here at the bottom right, we expected the diagonal term to be 4.55 times 10 to the -6. And remember, we just took those two values and did the following arithmetic. So remember, the ratio is equal to KII over DII. So what did we do in this case? We knew what the ratio is. We knew what KII is. So here, let me do this in orange again. So this is my KII, and then these are my ratios. So what I went ahead and I back calculated what DII is. DII is equal to KII over the ratio. And then I was expecting 4.55 e -6. So then when I use Nastran to actually output the diagonal value, I actually get 4.55 e -6. And now you can repeat the process. Here, there's a diagonal term that's -6.67. Let's go ahead and see the F06 file. Let me go ahead and show these side by side, actually. So scroll up here. Or actually, I'll leave it up to you to calculate these other ratios. But here, let me go back to this point. The whole goal in this part of the video was to explain what a pivot ratio was. This is basically the matrix diagonal to factor diagonal, which comes up a lot. So here, matrix factor diagonal. Matrix factor diagonal ratio. So when these are very high, when they're greater than the default value of E positive 7, you have a mechanism. So Nastran, during the procedure, when it's trying to find the solution, it calculates all of these matrix factor diagonal ratios. If they're very high, you have a mechanism. And when you have a mechanism, the inverse is undefined. Now, comment about this. Theoretically, the inverse of K is undefined if you have a mechanism. But you'll find out that you can, when you're dealing with these algorithms or in your computer, you can still find a solution. So the computer thinks that there is a solution, but we know that there is no solution, no unique solution. Just keep that in mind. When you use PARAM BAILOUT -1, this is what you're doing. When you first you get a mechanism, you get UFM 9050. This is a big warning telling you that, hey, the universe is undefined. You have a mechanism here. That's what we get, UFM 9050. But then we say, you know what? Still go forward with the solution. And it still will find a solution. But this will tell you one solution of many. So when we use PARAM BAILOUT, we say, okay, still find me the one solution out of many. And it still will find you a solution. If you recall, and I think it might be worth trying this again. Let's try that example where I had, this was defined as steel, the middle was defined as jello, and then the other piece was defined as steel also. So let's go ahead and look at this example. Or actually, no. Let's look at a different example. Let's look at the example where it's one material, but they're on rollers. That would be this other example, actually. I already have it loaded. Perfect. So let's go ahead and use it. So let's look at this scenario. So we have our pressure load. So we see here that it's unstable. So K1 is undefined. We know it's undefined. But the algorithm is still will find a solution. So here's that example. Let's look at the F06 file. All right, this was this example. Let's go ahead and rerun it actually. So we'll go ahead and do solution 101. Click apply. And let's look at the F06 file. So here we got UFM 9050. It's giving us a warning, hey, the stiffness matrix, the inverse, doesn't have a unique solution. But then what we're going to do is we're going to say, hey, you know what? Still go forward with the solution. And the algorithm will still go and try and find one solution for you. Now, this is one solution of many. So now if we look at the F06 file again, let me see if this happens. So the UFM 9050 is gone. It actually tried to perform the solution. So here we have some displacements, but let's go ahead and look at what the displacements look like in PARAM. So here, let's go ahead and delete the old H5 file. Let's go ahead and now look at the deflections. So this is one solution of many. So this is that one solution. So remember, this is supported on rollers. And this is what the solution looks like. This is moving left and right. And then is there actually any deflection? Oh, wow. So even though there's a pressure load here, there's no deformation in the Y direction. It's only translation in the Z and in the X direction. So we know that since we have an unstable structure, the inverse of the stiffness matrix is undefined. So there is not a unique solution. There's no solution, not a unique solution rather. But when you use PARAM BAILOUT, it still forces the algorithm to find a solution, one of many solutions. So that's what that one or not possible, but one of many solutions looks like. So I wanted to point that out. Okay, so where are we at with this? So we went over how to read this table. We went over this column. We went over the matrix factor diagonal ratio. If that's too high, you have a mechanism. The matrix diagonal is basically a value from the stiffness matrix. When you look at these two columns, grid point ID and degree of freedom, remember to do the following. find the node, look at the surrounding mesh, ask yourself why is that region a mechanism? And then the reason you should do this is because somewhere else in the model is causing the mechanism. So then in this example, what we did a lot was we used normal modes a lot. We looked at the 0 Hertz natural frequencies. We looked at the mode shapes. And that was very useful in identifying where exactly we have a very, or rather, we use these mode shapes to identify where we have instability, where we need more support, or where we have soft stiffness in the model. Let me look at the agenda just to see if there's anything else that I'm missing. Right, maybe we'll do a bonus round at this moment. Here, some of you might want to look at what the stiffness matrix looks like. So how do you do this? Let me go ahead and copy this unstable version. Before I do that, let me go ahead and look in here. So let me turn off PARAM BAILOUT -1. Let's go ahead and run this. Actually, let me look here. Let me go back to this example. Now, completely forgot what example this is. 77. Let me run it real quick. I'm trying to replicate the user federal message 9050. Okay, perfect. So that would be this. Okay, 229. Right, so this is the same message that we were discussing a moment ago. Here we get told that this matrix diagonal is at row 229. So you might be asking yourself, okay, what does the stiffness matrix look like? What does row 229 look like? What you can do is the following. You can copy this case control command. Let's go ahead and open it up. Let's go ahead and add it here. And let's run it. Now, what this command is going to do, it's going to write out an H5 file. So let me see if it's here. So this is what the H5 file looks like. It has this name. It ends with ODYS H5. Now, when you open this H5 file in HDF view, it's going to contain the stiffness matrix for this example. So here, if you look at the left branch, double click on KAA. Now let's look for row 229. And then let's go ahead and move over to column 229. So here is, all right, 5.135. Let me make sure this is the same one. Okay, perfect. So here, oh wow, this is something's off a little here. Oh right, I'm off. Okay, yeah. So the H5 file starts with index 0, but Nastran starts with index 1. So here, what I need to look at is row 228 and column 228. So here, the stiffness at row 228 and column 228 is 2.96 E10. And if you look here, so if you look at row 228, column 228, and KAA, you can see that it's the same stiffness value. So here, let's go ahead and copy this to the F06 file here on the right. So here you can see that when we use this command, we were able to output the stiffness matrix. And then here in the F06 file, we were told that the maximum diagonal to factor ratio happens in row number 229. So then I looked in the H5 file. Here, remember that the indices start with 0, so you have to offset. So here, instead of row 229, you're looking for row 228. So then we looked for row 228. We found that value. So that's the same value. What I wanted to do here was to prove to you that this matrix diagonal column or stiffness values from the K matrix. And then earlier in the presentation, you saw how I used this alter to output the D matrix to the F06 file. And then after that, we went through that whole long discussion on what the ratio equation is and so on and so on. So that was one of the last things I wanted to leave you off with. Now, let me see if there's anything else to cover here. So I have a few additional videos coming up. So there's going to be another video on the grid point singularity table, I think it's called. And then recently, while I was preparing for this video, I had to learn a little on DMAP. So another video is going to cover some details regarding how to interact with DMAP. This is not a deep dive into DMAP. It's just very introductory. And then I'm going to talk about the grid point singularity table. I don't know if it's actually here. Grid point. Let's see if it's actually in here. I guess it's not. But some of you may have seen this table before. It looks something like this. I think you get the point here. And then it looks a little like this also. Not exactly, but it resembles this. So right, in an upcoming video, I'm going to do a video on the grid point singularity table. I'm going to explain how to decipher that table. And then in another video, I'm going to discuss DMAP. This is not a full description of what DMAP is. It's just an introduction on how to interact with a DMAP to do very simple things. And then I think that's pretty much the end of everything I wanted to cover. I hope you found this discussion valuable. I know, especially if you're a new Nastran user, you're going to see user fatal message 9050 a lot. But the cause of it is actually very simple to understand. It's just not very clearly explained in other resources. So I wanted to take the time to help you understand what that fatal message is. I want to leave you off with these animations. Remember, if your structure is not properly supported, you're going to get a mechanism. If you're mixing very high stiffnesses with very low stiffnesses, you also get a mechanism. So that's everything I wanted to cover. As always, thank you for watching, and I'll stop here.